Hello students, welcome to the class of Control System 2. I am Priyanjali Mukherjee, Assistant Professor of Electrical Engineering Department of Narula Institute of Technology. Today we will discuss on the concept and the properties associated with the state equations. This video contains the state space equation, ABCD matrices, homogeneous and non-homogeneous equation, the solution of state space equations, and obtaining the state space equation from differential equations. State space equation. The state equation actually shows the relationship between the system's current state and its input and the future state of the system. Whereas the output equation describes the relationship between the system state and its input and the output. Now the state of the control system at time t is equal to t0 is the smallest set of variables, which is known as the state variables. And the knowledge of these state variables along with the knowledge of the inputs at t is equal to t0 is sufficient to determine the output dynamics of the system at any time t greater than is equal to t0. And in other words, we can say that the state of the system represents the minimum amount of the information which is required to know about the system at t0 so that the future behavior can be found out with the reference to the input before t is equal to t0. So these state space equations are this x dot is equal to ax plus bu t and y is equal to cx plus dut. Now this x dot is equal to ax plus but is known as the state equation, whereas yt is equal to cxt plus dut known as the output equation. Now the simulation can be done by using the integration terms in the diagram or the state diagram, and output of the integrators are actually the state variables which can define the internal state of the system. Now if the number of state variable is 2 for a system, then the number of integrator required is equal to 2. So the number of state variable represents the number of integrator required to represent the system. So here we can see that x dot is n by 1 vector, whereas A is a n by n matrix and B is n by 1 vector and U is the input. And from the output equation we can say that y is 1 by n vector, whereas x is the x1 x2 up to xn, whereas C is the n cross 1 matrix and the D may be 0 and ut is the input again. So next is the ABCD matrix. Now the output variables, which are denoted by actually y1 y2 up to yn, and the output variables at time are the linear combination of input and the state variable at time t. So the yt is equal to cx plus dut, and in this y vector, y is the output vector, c is output matrix and d is the transmission matrix or input output coupling matrix. Now the system matrix is A and it relates how the current state affects the change state x dash. And if the state changes is not dependent on the current state, then A becomes the zero matrix. And the B matrix is known as the input coupling matrix or the control matrix, and it determines how the system input affects the state change. Next is C matrix. C matrix is known as the output coupling matrix or the output matrix, and it determines the relationship between the system state and the system output. And the final one is the matrix D, and it is known as the input output coupling matrix or the feed forward matrix. It allows for the system input to affect the system output directly. Now the term DUT indicates the direct coupling of the input to the output. The direct coupling of the input to the output is very rare in the control system. So generally D becomes 0. And when D becomes 0, the state model of the linear invariant system can be given as x dot is equal to ax plus but and y is equal to only cx. So next is the homogeneous equation and the non-homogeneous equation. Now to represent the state space, we can use the dynamics of a control system, which can be described by the first order differential equation. It may be integral differential equation also, and the differential equations can be depicted diagrammatically using the integrator summers and the constant multipliers in the form of the block diagram or the signal flow graphs. Now during the state space representation, there are basically two types of the equations. One is the homogeneous equation and another is the non-homogeneous equation. Now using these two equations, we can identify the behavior of the xt and yt throughout the system. So what is homogeneous equation? So homogeneous equation means there are actually, if we consider the total response, then this total response will be divided into two halves. One is the response where the input is become 0, and another is the response where we are considering that input is present but the initial state is equal to 0. So if we consider any initial state and the initial state is equal to 0, then we can say that x dot is equal to ax plus bu, and u is equal to 0, so x dot t become ax. Now this x dot t equal to ax is actually the homogeneous part, and the but term is the non-homogeneous part of the state equation, and this is also known as the forcing function of the system. So if a homogeneous equation is there, that means ut becomes 0, the state equation becomes x dot is equal to ax, and the solution of this state equation gives us the unforced response of the control system, and it is governed by the initial conditions only. And now second one is possible if the input u is specified and it is not equal to 0, then the response which can be obtained is known as the forced response. So the total response of a system has been divided into two parts. One is the zero state response and another is the zero input response. And zero state response means the output of the system is obtained due to the inputs only, and all the initial conditions of the system are 0. And zero input response represents the response due to the initial conditions only, where we have assumed all the inputs to the system is equal to 0. So these are the basics of the homogeneous and non-homogeneous equation, and we can use the Laplace transform method to solve the homogeneous and non-homogeneous equation. So the total response of the linear system becomes the zero input response and zero state response. That is the summation of zero input and zero state. So xt in mathematically can be represented as e to the power at into x0. x0 is the initial state plus integration of e to the power at minus tau bu tau d tau. Integration from 0 to t. And if we consider the non-zero initial time, then we can write it is equal to e to the power at minus t0 into xt0 plus t0 to t e to the power at minus tau bu tau d tau. So this is the solution of the state equation. Next is the homogeneous equation solution. So if we consider the state equations, then x dot t or dxt dt equal to axt plus but, whereas the yt equal to cxt plus dut. So now the system becomes the homogeneous when the ut part will be 0. So we can write x dot t is equal to a into xt. So if x dot t equal to xt, then we can take the Laplace transform in the both side, assuming that initial conditions are present. So we can write s into xs minus x of 0 equal to a into x0. So when xxx minus x0 equal to axs, we can find out xs like this: si minus a inverse into x of 0. X of 0 is the initial condition. So this one is the solution of homogeneous equation. And next is the non-homogeneous equation. So if we consider the non-homogeneous equation, that means both the term axt and but will be present. So next we will apply the Laplace transform in the both side of this state equation. X dot t is equal to axt plus but. So if we consider the initial conditions are not equal to 0, then we can write si minus a into xs equal to x0 plus bus, where this x0 is the initial condition. And xs becomes si minus a inverse into x0 plus si minus a inverse into bus. So next we can take Laplace inverse to represent the x of t, and it gives the result in two halves. One is the zero input response, that is the first term where it is dependent upon the initial state, and next is the zero state response where it is do not depend on the initial state. So this one is the zero state response and this one is the zero input response, and we can say that the overall response of the system can be divided into two parts. One is the zero input, another is the zero state response. So next is the obtaining the state space equation from the differential equations. So let's see, we have considered one third order differential equation over here, which is d cube yt dt cube plus s squared d square y a2 d2y dt square plus a1 dy dt plus a0 yt equal to ut. So ut is considered here as the input and yt is the output. So to find out the state space equation from this differential equation, first we have to select the state variables. So we can select the state variable in this format: x1 equal to y of t, where y is the output. So if x1 is equal to yt, we can say that x2, which is the x1 dot, that means x1 can be derived by the integration of x2. So x2 equal to dy dt, and x3 becomes d square y dt square. So now we can use the three first order equation in this form. Thus x1 dash equal to x2, x2 dot or x2 dash is equal to x3, and x3 dash is equal to d3y dt cube. And this d3y dt cube can be written as u of t minus of a0 yt minus a1 dy dt, which is actually x2, and minus a2 into d square y dt square. So we have defined the state vector x in terms of the individual x components. So we can assemble the state space equation for this system, and it can be represented by x dash is equal to 0 1 0 0 0 1 minus a0 minus a1 minus a2. Similarly, the B matrix can be defined as the 0, 0, 1 and C matrix is 1, 0, 0. And here we have not considered the D because D becomes 0 over here. So using this method, we can easily find out the state space equation from the differential equations. Let's put the values of the coefficients. So here it is, values are given as 6, 11 and 10, the coefficients of d square by dt square, dy dt and y, and ut is 8 ut. So y is the output over here and u is the input to this system, and we have to obtain the state space of the given system. So first we will assign the state variables. So first we will consider x1 is equal to y. So if x1 equal to y, then x2 is the integration. During this integration of x2 we will get x1, or x1 dot is equal to x2, which is equal to y dot. And similarly x2 can be obtained by integrating the term x3. So x3 is equal to x2 dot and x2 dot is equal to y double dot. So we can write in this formulation x1 dot is equal to x2, whereas x2 dot equal to x3 and x3 dot equal to 8 ut minus 10x1 minus 11x2 minus 6x3. So now we can use these three equations into the state equation, and we can convert this in the vector matrix form by this previous method. And y is the only x1. So C matrix becomes 1, 0, 0. Whereas the system matrix is 0, 1, 0. Second is 0, 0, 1. And final one is the minus 10, minus 11 and minus 6, which is actually the coefficients of the y dot and y double dot. Similarly, B can be found out by 0, 0, 8. 8 is multiplied with ut, that's why we are getting the B matrix as 0, 0, 8. So after this video lecture, I hope you have a clear idea about today's topic. Now we will go through some question answer session in context of this video lecture. So you are requested to go through it gradually and solve it by your own. Answers are attached at the end of each question.